All right. Any questions from prior stuff before we jump into PA3? All right. Well, let's get to it. So PA3 is about decision trees. So binary trees, but they're not binary search trees. They're yes/no trees. So our goal is to implement a decision tree, be able to save it to a file, read it from a file, update it, and use it to play a game of 20 questions. So 20 questions game, if you're not familiar, right, one person, this is going to be the human, thinks of an object. And the other player, which is the computer, tries to guess what that object is by asking yes/no questions. And you answer truthfully the yes/no questions, and that should help the person trying to guess narrow down what it is you're thinking of. And the goal is within 20 questions, can the other person guess what you're thinking of? So you're going to implement a computerized version of this where the computer will be trying to guess what you're thinking of, okay? So make sure you get the order right. The person playing the game thinks of an object, the computer tries to guess it, okay? So the computer will be asking yes/no questions, and the user will be typing in yes or no, and going from there. All right, so this is like the 20 questions game. We're not limiting you to 20 questions though, okay? That's just what the game is called. So you're going to implement a tree, which is what we call a decision tree. And let me show you how this relates to playing 20 questions. So so we play 20 questions, and you say, I'm thinking of an object. And I say, okay, is your object a pencil? And you say no because you were thinking of a dog. Okay? So I did not guess correctly. So I'm going to say, tell me a question for which yes is a dog and no is a pencil. And you're going to say, you should have asked me, does it bark? Okay, I'm going to code that piece of information you just gave me into a tree. So here's what my tree is going to look like. Does it bark? And if you say yes, I'm going to say you were thinking of a dog. And if you say no, I'm going to say you were thinking of a pencil. Okay, with this coded information, I can do a better job playing 20 questions. So I go up to somebody else and they're thinking of something. And I'll say, does it bark? And they'll say no, and I'll say, aha, you were thinking of a pencil, weren't you? And they'll say, no, I was thinking of a rock. And I'll say, okay, tell me a question for which yes is a rock and no is a pencil. And they might say, can you hurt, is it heavy? Okay. So instead of this being pencil, I'm going to make a new node, which is a question, is it heavy? And if the answer is yes, I'm going to say you were thinking of a rock. And if the answer is no, I'm going to say you were thinking of a pencil. And now I have a better decision tree. And if somebody is thinking of a dog or a rock or a pencil, I can figure out what they were thinking of. So if you are thinking of a dog, my first question is, does it bark? You say yes, I'm going to say dog. If you're thinking of a rock, does it bark? No. Is it heavy? Yes, it's a rock. If you're thinking of a pencil, does it bark? No. Is it heavy? No. You must be thinking of a pencil. But of course, if you're thinking of a cat, does it bark? No. Is it heavy? No. It must be a pencil. No, it's a cat. Okay, well, give me another question. So, does it meow? And if it does, it's a cat. And if it doesn't, it's a pencil. So the more you play this game, the better it gets, right? At first, it's going to be really, really bad at figuring out what you're thinking of because it only knows a few possible answers. But the more you play it, the more this tree grows, the better it gets. Okay, if this was a nice, full, fluffy tree, and it was 20 levels deep, right, you could get from the root to a leaf node in 20 questions. And if it's 20 levels deep and it's nice and full and fluffy, how many nodes does it have at the bottom? 2 to the 20th. That's approximately 1 million. So in a decision tree of height 20, we can code 1 million different things. And there's a path of 20 questions that will take you to each of those million things. And so we can differentiate a lot of different objects. It's hard to come up with 1 million different things, depending on how finely you granulated, right? We could have a dog named Barney and a dog named Betty, and those might be different dogs, you know. Could have Deputy Dog. But this is a really powerful looking system, and it really is uncanny how well it starts to work after a little bit of training. So this is what we're going to implement. So we're going to need to code a decision tree. We're going to need to be able to store this decision tree in a file, pull it back from the file, and do these updates to it so that when it's wrong, we can improve the tree and then write that new improved tree out to our file. And we need to use this tree to play the game, which is really just, you know, reading off the questions and moving down the tree based on the yes/no answers. All right, so what are the details here? You implement a binary tree. So I'm saying each node contains 2 pieces of data, a string of text and a flag indicating whether it's a question or an answer. In practice, you know, all our answers are leaf nodes, okay? But go ahead and put 2 fields in each node, the actual text and then something that's a flag that says, is this a question or an answer? It'll make the coding a little simpler. All right, so we've got a binary tree. Each node has 2 pieces of data, which is the text and then a flag saying question or answer. And then it has 2 children called yes or no. I want yes to be on the left, no to be on the right. If you switch those, this will not work. Okay. So to play the game, start at the root, which is a question, ask that question, wait for a yes/no response, and then move down to either the left or the right. Keep doing this until you get to a leaf node. At that point, say, I've got an answer. Tell them what the answer is. See if you were correct or not. If you were correct, perfect. The machine outthought the human. If it was incorrect, ask for a new question to determine the difference, to discriminate between the correct and incorrect answer. Make a new node, put it into the tree, and then you can play the game again. Okay, so the decision tree file is a file called 20q.txt, sitting in your current directory. And there's a sample version of this available on the server, so you can download that and you can use that as your starting database. And at the end of the game, if you modify the tree, you should write the new modified tree back into that same file. Okay. Additionally, you can use a different database file. So when you run your program, if you put a command line argument after it, that specifies the name of a file other than 20q.txt. So you can point this at different trees, different files containing decision trees. All right, so here's 20q.txt to start with, 6 lines. A root node, a yes answer, and a no answer. Is it an animal? Yes, it's a dog. No, it's a rock. Okay, that's our sort of starting point. So is it an animal? Yes, it's a dog. No, it's a rock. And you can start with whatever tree you want, right? Your assessment for this is not the decision tree, right? It's the code. So I'm going to test it with different decision trees in different files. But a good starting initial database would be this, 6 lines, okay? And that's the one on the server. You can work on this in pieces, right? One way to do this is not to worry about the input and output of the tree, because that part is trickier than some of the other pieces. So you could just build this tree, right? Make a node with dog, make a node with rock, make a node with is it an animal, set this node's left to that, right to that, or yes and no to that and that. Just cobble it together with a bunch of assignment statements, same thing we did in 222, right? And then develop the code for playing the game, for adjusting the tree at the end, and so on. And don't worry about the file I/O. Okay, that's one way to break this down. Do the file I/O separately. So hardwire that, you can play the game. You can use things like scanner, PrintWriter, string, these built-in methods. But you got to make your own tree class, got to do your own file parsing, got to do your own playing of the game, and so on. So that has to be your own code. But you can use scanner and PrintWriter to do input and output. We're going to talk about PrintWriter in a few minutes. Okay, stay away from Eclipse. We'll use Eclipse for programming assignment 4. We'll be going GUI. But for now, stick to the command line. Okay, good practice. So your main class, the class that contains your main method, is going to be called PA3. So it's got to sit in a file called pa3.java. And it should be executable by just saying java pa3. And it should open 20q.txt in the current directory and suck that in and just go to town. I'm going to take this out. It should always exist. Okay, you can assume that that file exists. So I'll take this out of the description. I can also run PA3 by saying Java PA3 and putting in the name of a different file, which should be a database file. And it should read from there and play. Let me make a note. Alright, so I'm going to give you a lot of information about this that's not written in this specification, okay? So the details are being given in class right now, so make sure you're getting those, because there's not all the information in this written description. There's a pair of databases on the server, 20q.txt, that's that 6-liner above. 20qbig.txt has 40,000 lines in it. Okay, it was offered to me by a former student who went to UW and had to do this assignment, and they were using this crowdsourced database. So we'll play around with 20qbig in a few minutes. So you should submit pa3.java and any other classes that you need. Make sure all of the classes are there. You're probably going to have a separate class for the decision tree, a separate class for the nodes of the decision tree. You may have a separate class for processing the file. It's totally up to you, okay? But make sure all of the classes that I need to compile and run your program are sitting in that top level of the Git repository, okay? Whatever you submit, download it, clone it to a new directory, try to compile all the pieces, get rid of all the .class files, do the Java C commands to compile, and then try to execute, okay? Replicate what I'm going to do when I grade. So grading, right, push it in the repository, CSE223 pa3.git. No surprises there. Okay, grading. If your project can be downloaded and compiles, you get 20 points. So make sure you have something up there that doesn't have syntax errors. If when I run the program it asks questions and at some point makes a guess, that's worth 10 points. So if it's doing something along the lines of playing the game, okay, you're up to 30 points. If it actually follows what's in the database file, if it actually follows the decision tree that's been written in the file, that gets you up to 60 points. Okay, so that's the heart of the program, is reading the decision tree from a file and then playing the game accordingly. Alright, if I can specify an alternate database on the command line, that's 10 points. That is not a showstopper for you, okay? Because chances are, you're going to do something like string dB equals, what do they call it, 20Q or Q20? 20Q. 20Q dot txt, right? Don't hardwire 20Q.txt in the middle of a file, in the middle of a scanner constructor. Stick it in a variable. And now to process your arguments, right, if args.length equals 1, dB equals args bracket 0. That's all you need to process the command line argument. Check to see if there's an args bracket 0, and if there is, set your database equal to that. And now you got an extra 10 points. You're up to 70 points already. Okay, 15 points for being able to update the database if the final guess was wrong. And we still have to talk about the details of that. And then 15 points for style considerations, consistent indenting and placing of brackets, comments on your code, introductory comment block before each method, and introductory comment block before the entire class. Right? This is for each class. So if you have, you know, main class that runs your PA3, right? PA3.class. If you've got a decision tree.class, if you've got a class named decision tree node and a class named ingest, right? Comment block for each of those. Okay, and this comment block, this is a really good place to put your name. Make sure your name is in there. Okay, you got to have all of these to get your 15 style points. And then submission, CSC 223 PA3, keep all of your .java code in the top level repository. And I'll pull them from there. I'll get rid of everything that's not a .java. I'll compile it and run it. So there's a comment in chat which says, if not, question mark. I don't know what that if not refers to. All right, so let's play this. So I'm going to pull down the 20Q file, and it's got our 6 lines of input. Is it an animal? If yes, it's a dog. If no, it's a rock. If you don't know how to use SFTP, by the way, dig into it, right? It's really easy. SFTP, username at linuxengrcs.com. You can CD, you can ls, you can move around the remote directory, and then when you want to pull a file down, just say get and the name of the file, and it'll copy it into your current directory. You can also say like LCD for local current directory or LLS for local ls. It's a really simple tool. It's been around for decades, super stable, very secure. If there's no arguments on the command, then it's just going to read from 20q.txt. So the initial decision tree should be read from a file 20q.txt. The name of the database should be modifiable by a single command line argument, but if there's no argument, just read from the default file. Alright, so let's play this. Let's do Java PA3. No argument, it's reading from 20q.txt. Think of an object and I'll try to guess what you're thinking of. Okay, I am thinking of, what am I thinking of? I'm thinking of a car, because I'm staring at a parking lot. Okay, so I'm thinking of a car. Is it an animal? No. Okay, I've got it. Is it a rock? No, it's not. What were you thinking of? A car. Okay, give me a yes-no question for which yes means a car and no means a rock. So, can you sit inside it? Okay. So now let's take a look at 20q.txt, and it's different. It still has the original question, is it an animal? Yes, it's dog. But now there's a new question, can you sit inside it? And it says car and rock. So is it an animal? No. Can you sit inside it? Yes. Is it a car? Yes. Is it an animal? No. Can you sit inside it? No. Is it a rock? Yes. Okay, so it's a little better now. Yes. Okay, let's say I'm thinking of a cow. So is it an animal? Yes. Is it a dog? No. Or are you thinking of a cow? Please type a question for it. Yes means a cow and no means a dog. Does it say moo? Okay, now my database is a little bigger. And don't try too hard to understand the contents of this file, okay? You don't have to. The way we're going to describe how to work with this file, you don't need to understand why this question is down here and this question is up here, okay? Working with this file directly, especially as it gets large, is not what you want to do, okay? I'm going to show you how to work with this recursively. And recursively it's going to be very easy, which means non-recursively is going to be very, very difficult. Don't worry about, right, when you have to add a new question, don't try to figure out which line in here you should add that new question to. That's too much work and you're probably not going to do it in the right place. Okay, and it's unnecessary. But I'm looking at this just to show you that the file is growing, right? It's 14 lines right now. So our tree has 7 nodes in it. So is it an animal? Yes. I'm thinking of a cat. Does it say moo? No. I've got it. It's a dog? No. What are you thinking of? It's a cat. Question for which yes means a cat and no means a dog. Does it drink milk? Alright. So now we've got 18 lines in our file. Right? So this is growing. And it's getting better. Okay, so let's run this on 20Q big. So I need a volunteer who wants to think of an animal. Okay, this database is only for creatures, not for things. So who wants to think of an animal and see how this does? But don't tell us what it is. Sorry. Do you want to think of a different animal? Okay, cool. If you want to turn on your speaker so we can all hear your answers, that's cool. If not, I can read them off from the chat, as long as I don't lose track. Alright, so you're thinking of an animal, right? You go on microphone or not? Oh, I don't have a mic. Okay, I'll try to keep track of your answers as they come in and I'll read them aloud. Okay, so you're thinking of an animal, right? So can it fly? Okay, she says no. Is it a very small animal? Yes. Does it live in trees? No. Is it a type of dog? Nope. Does it build dams? Nope. Does it have a long tail? Does it eat dirt? I guess some animals do. No. Is it a native Australian animal? Nope. Does it live in a cold climate? It's a strange line of questioning. Does it smell bad? Does it lay eggs? Interesting. Do they plunge into the sea and kill themselves? That's a bummer. Glad to hear that. Does it have fins? Yes. Does it look like it's wearing a tuxedo? Nope. I think I've got it. Is it a fish? Oh, that's a boring answer. Is it a fish? Yes. Well, that's not a terribly great answer it came up with, but I guess technically that's correct. Catfish, okay. Do catfish smell bad? I didn't realize that. Interesting. Okay. So this morning somebody thought of a Komodo dragon and it actually nailed that one exactly, which was impressive. So this is a crowdsourced, so thank you for doing that, for being the brave volunteer. So this is, I believe, a crowdsourced database, right? And, you know, lots of people play it and they put in lots of information. But it's, you know, questionable variable quality, right? And it's got lots of interesting answers in it. It's got some Pokemon answers and some, I think the Predator from Alien is in here, or the Alien from Predator is in here, and all kinds of stuff like that. So I don't suggest using this to debug and develop your code, okay? Use this just mostly for fun at the end, and to show off your code to people, and if you want to make sure that it doesn't blow up with a large database, right? But for developing your code, you know, start with a simple database, either the one I've given you or one of your own choosing, and build it up from there, okay? Snowman. Alright, so, and like I say, both of those are available on the Linux server under /temp. Make copies of them. I made them read-only, so they can't get clobbered. So copy those over into your directory and play with them as you like. Alright, let's talk about reading in the decision tree from a file and writing it back out to a file. Okay, writing it is easy. Write it out in pre-order, node left, right. Okay, so if your tree looks like this, you know, is it furry? Yes. Can it swim? Yes, it's a seal. No, it's a cat. If it's not furry, it's a laptop. Okay, write this out, node left, right. Write this node, write the left subtree, write the right subtree. Okay, just plain old pre-order traversal from 222. And when you write it, right, for each node you want to write either a Q colon followed by the text, or an A colon followed by the text. Q for a question, A for an answer. And if you put a flag in these nodes to indicate whether it's a question or an answer, you can use that to write this out. Otherwise, you have to check to see if you have any children. And if you don't, then you're an answer node. So you can do it either way. So writing from the decision tree to the file, pretty straightforward. It's just a recursive pre-order traversal. Ingesting is a little more interesting. Okay? Because it's written in pre-order, the node of a subtree is going to appear before its children appear. In fact, it's going to appear immediately before its children. So we can ingest some way like this. Let's say node ingest. Okay, so open up your file right? Using a scanner and a file constructor. So you have a scanner object, and you can make that global in your class, or you can pass it around. It's up to you. Let me just assume it's global for now. So I'm going to write a method called ingest, and the goal of ingest is to start at the current point you're at in the file and read in a decision tree. Okay? You may not read the entire file. You're just going to start wherever you happen to be in the file and keep reading and building a tree until you have a tree. So how do you know that you have a decision tree? Well, you've read a root node, you've read a left subtree, and you've read a right subtree. So if our file looks like this, and I happen to be right here in my tree and I call my ingest method, it's going to read these first two lines. That's going to be a question. That'll be the root node of my tree. It's going to read these lines. That's the left subtree. It's going to read these lines. That's the right subtree. And it's done. It's going to consume these 6 lines from my input file, my scanner. It's going to build a tree with 1 question and 2 answers. And it's going to return. And it's going to return the root of this little 3-node tree. Okay, so ingest will start at the current location in your input file, and it will ingest a binary decision tree. And here's how we do our ingest. So read read 2 lines from the file. If it's an answer, make an answer node and return it. So if I happen to be right here in the file and I call ingest, I should consume 2 lines of my file, A and dog. I should notice that's an answer. I should make a single node containing the word dog, mark it as an answer, set the yes and no children to null, and return that as the value of ingest. Right, so that call to ingest would only consume 2 lines from the file, and I would get back an answer node with no children. Okay, so if it's an answer, make an answer node and return it. Otherwise, ingest, right, call our ingest method. Well, okay, make a new node, make a new question node, use the text you just read. Right, so you read 2 lines, turn that into a question node. Call your ingest method, and whatever ingest returns, set your yes child to that return value. And then call ingest once more and set your no child equal to that return value. And then return the new node. So it's a really short procedure, and it's highly recursive. Basically, read the first piece from your file. If it's an answer, just return that as a node. If it's a question, store that in the root of a new node, and then call ingest twice. Take the thing you get back from the first call, have the yes node point to that. Take the thing from the second call, have the no child point to that. And then return your node. And this is kind of one of these things you really don't want to think about too deeply while you're writing it. You can think about it before, you can think about it after, but while you're writing it, you really just want to follow the algorithm, okay? Because it's recursive, and recursive stuff, if you start thinking about it, you end up not following the algorithm, and it ends up getting into usually a big quagmire, okay? So think about the algorithm, study it, convince yourself it works, talk to friends about it, whiteboard it, all of that stuff, right? And then code it faithfully. And if you don't believe this is a good algorithm, right, work with this. Don't start coding this and then start changing the code because you feel like it should be something different, okay? Do that on paper, do your analysis. And this should successfully ingest, and if you do this on a properly made decision tree file, if you start at the beginning of the file and you say ingest, you should end up with a complete decision tree, and you should end up at the end of the file. You should never actually go beyond the end of the file if this works correctly. And you can assume the decision trees I'm going to test with are proper decision trees. Okay, no errors, no missing lines, and so on. So theoretically, you're never going to hit end of file when you do this. Okay, but it takes some faith. All right, questions about that? Okay, so let's just take a look at this sample decision tree file. So suppose we use our ingest algorithm on this file. So we're going to read the first two lines from the file. So we'll read that question, is it an animal? And we'll turn that into a node. Okay, if it's an answer, we would just be done, but it's not, it's a question. So we're going to make a new node with the question, is it an animal? And now we're going to call ingest, and whatever ingest returns, that's going to come off the yes branch. So we're going to call ingest sitting at this line of the file. Okay, so we're down one level in recursion. And our call to ingest says read two lines from the file. So it reads, question, does it meow? And that's a question, so it's going to make a new node. Does it meow? And then it's going to call ingest again. So it's going to call ingest starting from this point. So we're another level of recursion down. We're going to read two lines, which is answer cat. So it's an answer. We're just going to make an empty node containing just that answer. So it's a cat with no children. Sorry, I'm missing the action here. Okay, so that was our original node, is it an animal? And we made a recursive call to ingest, which found a question, does it meow? Which said, let's call ingest and take the return and set it equal to the yes node. And so we called ingest again. We were at this point where it found an answer node, which was cat. So it made a cat and it returned. Okay, we were calling ingest to assign the yes node of this, does it meow? So we come back from that first call to ingest, and yes points to this. Now we have to make another call to ingest to assign to the no node. So we go back to our file, we ingested answer cat. Here we find a question, does it say moo? So what are we supposed to do? Make a node that says, does it say moo? And call ingest, assign the result to the yes node. So we ingest answer cow, which will make a single node containing cow, and we say set the yes node equal to that. Now we call ingest again to set a value for the no node. So we consume answer dog, right? We ingest, there's an answer line, so we make a node that says dog. We come back from ingest, we set the no value equal to that. Okay, we have finished the call to ingest that we did when we were setting up this does it meow node. Right, we called ingest to set up this. We called ingest again and we started recursively doing all of this. We're back from that call to ingest, we set the no node equal to that. Okay, all of this was being done in our first call to ingest, which read in 2 lines, is it an animal? And then said call ingest and said yes equal to the result. We just came back from that first call to ingest, right? And so our yes node is equal to what that call returned. And now we have to call ingest a second time to set the no node. And then we're done. Okay, well we call ingest, we're sitting right here down at answer rock. So what does our ingest routine do? It reads in those 2 lines, it says it's an answer node, so it makes a node rock, and it returns it. We're back from this call to ingest, we set the no node equal to that, and now we're done. We return the new node. This is the tree that we get back from our 1 call to ingest in our main program. And it's our decision tree. If it's not an animal, it's a rock. If it is, does it meow? It's a cat. No. Does it say moo? Yes, it's a cow. No, it's a dog. All right. So ingest using this recursive algorithm, write by using node left-right traversal. And it should just sort of magically take care of itself. All right, let me talk about writing. Oh boy. All right, so main writing, very simple. Import java.io.PrintWriter. If we want to write to a file, construct a PrintWriter device with the name of the file that you want to create. mynewfile.txt. And then we can say things like out.println. This is a new line of text in my new file. I'll write that out 5 times, and then I'll close my file. Okay, one complication, PrintWriter can throw an error, okay, because it may not be able to create that file. It might be in a directory it doesn't have write permission to, and so on. So this PrintWriter construction has to go inside a try-catch block, and don't declare your out object inside a try-catch block because it becomes local. So out is an object PrintWriter type, construct it, mynewfile.txt, and then we can just say print line, and we can put whatever we want in there, and then close it when you're done. Okay, so there's our main class. Let's go ahead and run it. And now we have a new file in here called mynewfile.txt, which has our 5 lines of text. And PrintWriter, right, it has a whole bunch of methods available to it. So you can print line, you can print F to do C-type things. You can print different types of objects, you can print strings and so on and so forth. All the stuff that you can do with system.out.println, printf, and so on, you can do with a PrintWriter object. And it's a really easy way to do output. Okay, so right? Construct it with a file name, which can have a path if you like, and then mostly we're just going to do print line because we're just writing a line at a time. That's enough to do output. You can use scanners to do input. That should be enough to get you on the air with a preliminary version of 20 questions. All right, so finish up PA2 if you haven't already done that. Try to get working on PA3 as soon as possible. Come to class tomorrow if you want to ask questions. It'll be an open lab, so take advantage of that if you like. I will see you next time. Have a great afternoon. If I don't see you tomorrow, have a great weekend, and I'll catch you later on.